Hello, my name is Kevin Duarte. I'm a PhD student from the Center of Research in Computer Vision at the University of Central Florida. I will present our work, Partial Label Masking for Imbalanced Multi-Label Classification. This work is done in collaboration with faculty Yogeshwar Watt and Professor Mubarak Shah. This work deals with learning from imbalanced data. Often, real-world datasets contain a long-tail class distribution where some classes contain many samples and others contain only a few samples. Those frequently occurring classes are often called head classes, while infrequent classes are called tail classes. Learning from imbalanced datasets tends to cause classifiers to generalize poorly on samples from the tail of the distribution. This is a fundamental machine learning problem which has been heavily studied. Although there have been various approaches that attempt to solve this problem, there are two commonly used methods, reweighting and resampling. Loss reweighting involves adjusting the loss function based on the number of samples for each class. Often, loss for head classes is reduced while the impact of the loss for tail classes is increased. Resampling attempts to reduce the amount of data imbalance seen by the network during training. Undersampling consists of removing samples from frequent classes, while oversampling involves repeating or generating tail class samples. In this work, we focus on the problem of multi-label imbalance. Multi-label datasets consist of samples which contain multiple classes. Classifiers trained on multi-label data often assume classes are independent. Their output probabilities are generated from a sigmoid activation rather than softmax, and they are trained using binary cross-entropy rather than softmax cross-entropy. These differences from single-label datasets often lead common methods for imbalance to fail. Loss reweighting fails because it increases the weight for negative samples of the tail class. Here we show the standard weighted binary cross-entropy where alpha is the inverse number of positive samples. Since tail classes often contain drastically more negative samples than positive samples, the weight has a much larger impact on the second half of this term. This causes networks to underpredict such classes at test time. Resampling multi-label data is difficult because of the co-occurrence of frequent and infrequent classes. For example, this collection of 6 samples contains 5 classes. One can undersample the data, but due to the co-occurrence between the person class and the phone and hairdryer classes, the undersampled dataset is still imbalanced. Imbalance is often measured between the number of positive samples for each class. However, this is not the only form of imbalance present within long-tail datasets. In multi-label datasets, there is often a drastic imbalance between the number of positive and negative samples for each class. The ratio of positive to negative samples is often larger for head classes than for tail classes. For example, in the artificially constructed long-tail multi-MNIST dataset, it can be seen that this ratio for the most frequent class is greater than 1:1, and the ratio for the least frequent class is less than 1 positive sample for every 138 negative samples. This imbalance often leads classifiers to underpredict on infrequent classes and overpredict on frequent classes. To illustrate this, we depict the distribution of probability outputs for a classifier trained using binary cross-entropy loss. For positive samples of the tail class, the classifier often predicts probabilities lower than 0.5. Conversely, for negative samples of the head class, the classifier predicts probabilities larger than 0.5. I will now present our approach called partial label masking, which attempts to solve this issue. Our proposed approach reduces the imbalance in the ratio of positive to negative samples, which in turn leads to reduced over and under predictions for frequent and infrequent classes respectively. This approach consists of stochastically masking individual labels to reduce the impact of this ratio. We can mask positive labels for head classes and negative labels for tail classes to ensure the ratio is less imbalanced across different classes. For example, if we wanted to ensure a 1:1 ratio of positives to negatives for each class, we can perform masking as depicted in this graph. For classes with more positives and negatives, positive samples will be masked. Conversely, negative samples will be masked for those infrequent classes which have a very low ratio. In our approach, we do not use a fixed ratio, but rather attempt to find an optimal ratio for each class based on the classifier's output probabilities. Ideally, the ratio should be set to minimize over and under predictions across all classes. I will now describe the proposed partial label masking method in more detail. Since this work deals with multi-label imbalance, the label for a given sample y is a binary vector of length c, where 1 denotes that a class is present within the sample and 0 denotes that the class is not present. The network predicts a vector of c probabilities denoted by y hat. We also denote the ratio of positives to negative samples for a class C as R sub c. Our method masks labels to ensure that a given ratio is used, which we call the ideal ratio or R hat. Our approach consists of masking the loss computation such that certain positive and negative samples do not contribute to the training. Given a loss defined here, where each class's loss is computed independently and summed to obtain a final loss, we can mask the contribution of individual classes as follows. Here, G is a binary mask where 1 denotes that the loss is used and 0 denotes that the loss is ignored for the given class. This is a general formulation that can be used for any loss which sums over the classes, like binary cross-entropy and focal loss. The mask G is generated stochastically as follows. Here, the probabilities R hat over R and R over R hat ensure that the ratio of positive to negative labels on which the loss is calculated is set to the ideal ratio R hat. Now the question becomes, what is the ideal ratio and how can it be determined? Selecting an optimal ratio is non-trivial, as it can depend on the type of classifier used, the type of data seen by the network, and the level of imbalance within the dataset. We propose a method that estimates this ideal ratio based on the performance of the classifier. It attempts to minimize over and under prediction across all classes. If the network overpredicts a given class, then the ratio should be decreased for that class. Conversely, if the network underpredicts a given class, then the ratio should be increased. This change or adaptation of the ratio occurs throughout network training. I will now describe the procedure by which we perform the ratio adaptation. First, we construct distributions for the output probabilities and labels. This can be done by generating the normalized histogram of the output probabilities and labels values for positive and negative samples for a given class. These histograms represent discrete probability distributions. Here, P plus and P minus denote the distributions for the ground truth positive and negative labels respectively. P hat plus and P hat minus denote the distributions for network predictions on positive and negative samples respectively. We present example distributions constructed for the imbalanced multi-MNIST dataset. The positive distribution for the ground truth labels are presented here. The corresponding predicted probability distributions for 2 of the most frequent and 2 of the least frequent classes are presented here. It can be seen that distributions for the tail classes greatly differ from the ground truth distribution because the network often predicts low probabilities for samples with these classes, leading to underprediction. We also present the ground truth and output probability distributions for the negative samples. Here, the distribution for the head classes differ most from the ground truth due to overprediction from the network. Given these distributions, we can now attempt to change the ratio to minimize both under and over predictions. We first measure the difference between the distributions by calculating the KL divergence. We then normalize these divergences across all classes and combine the positive and negative divergences into a single term. This term tends to be high when the network underpredicts a class C and tends to be low when the network overpredicts that class. We can now use this metric to change the ratio accordingly. We use the following equation to update the ratio at each epoch t. When DC is greater than 0, then the ratio is increased as the network is overpredicting for that class. When D is less than 0, the ratio decreases as the network is underpredicting class C. If DC is 0, then there is neither over nor underprediction, so the ratio remains unchanged. Here, the lambda hyperparameter determines the rate of change of the ratio. We examine the importance of this hyperparameter later. Here we show the partial label masking training algorithm. First, the ideal ratio is initialized. It can be initialized to some fixed value across all classes, or the original dataset's ratio of positive to negative samples can be used. Then, for each epoch, we generate the masks for all samples using the given current ideal ratio. The network can now be trained using the partial label masking loss. Here, the probability outputs generated by the network are stored for the computation of the output probability distributions. When all data for that epoch has been sampled, we generate the ground truth and output probability distributions and compute their differences. Finally, we update the ratio accordingly and begin the next epoch. We find that this training procedure reduces under and over predictions for tail and head classes respectively. Here, we show output probability distributions obtained from standard binary cross-entropy loss as presented earlier. On the right, we present the output probability distributions obtained from a network trained using PLM. When trained using our method, we find that there is a large decrease in the number of underpredictions for the tail classes. There is also a slight decrease in the overpredictions for head classes. We evaluate partial label masking on 4 datasets and perform several ablations and analyses. First, we evaluate on the artificially imbalanced multi-MNIST dataset. We compare with the standard losses, binary cross-entropy, and focal loss, as well as with common methods for learning with imbalance, such as class balance, loss-free weighting, and undersampling. Across all metrics, using partial label masking leads to improved performance. This improvement is mostly found among the classes with the fewest number of training samples. We then evaluate on the large-scale multi-label image dataset MS-COCO. This dataset inherently has a large level of imbalance, making it a realistic benchmark for a multi-label imbalance method. Once again, we find that PLM leads to improved performance with respect to recall and F1 score, especially for tail classes. The precision slightly decreases because there is a large increase in a recall for the tail classes. Here, the 0-1 accuracy tends to fall when PLM is used. This can be attributed to the fact that the test set is also imbalanced, and 0-1 accuracy tends to favor performance on classes which have many samples in the test set. Although PLM is designed for multi-label imbalance, we find that it performs decently on single-label data. We evaluate on the artificially imbalanced CIFAR-10 dataset with varying levels of long-tail imbalance. PLM achieves strong performance when compared to the standard baselines and only slightly underperforms when compared to the recent state-of-the-art LDAM loss. We also evaluate on the artificially imbalanced CIFAR-100 dataset with varying levels of long-tail imbalance. Again, PLM outperforms standard baselines, but achieves similar scores to the LDAM loss. In general, we find that using binary cross-entropy with partial label masking tends to outperform focal loss with PLM when the imbalance is large. This is consistent with findings in previous works which suggest that focal loss is unable to handle such large amounts of imbalance. We include two ablations of our method. The first studies the rate of change of the ratio. Here, we find that the rate of change parameter lambda should be adjusted based on the dataset. Furthermore, we find that setting lambda to 0 and not changing the ratio, which is equivalent to using standard binary cross-entropy, underperforms when compared to both rapid and slow changes in the ratio. The second ablation is to determine what the ratio should be initialized as. If the ratio is set to the mean of all ratios, this would ensure that fewer positive samples are used for head classes and fewer negative samples are used by tail classes. Although this approach does improve performance, we find that initializing the ideal ratio to the dataset's ground truth ratio and letting it change over time leads to best results. We examine how the ratio changes throughout training. Here we present the change of the ratio over 90 epochs on the imbalanced multi-MNEST dataset. Note, the y-axis is log scale. Generally, our assumption holds. The ratio for head classes, in this case digits 0, 1, and 2, decreases because the network tends to overpredict these classes. On the other hand, the ratio for tail classes increases since these classes are often underpredicted. We continue our analysis of PLM by measuring the performance across classes of the CIFAR 10 dataset. Overall, the network trained using PLM improves performance on tail classes, especially when the imbalance is large. This performance improvement is also found on the MS-COCO dataset. Here, we present the F1 score for each class of the MS-COCO dataset, as well as their number of samples. For the 15 classes with the fewest number of samples, using partial label masking leads to improved results. Furthermore, we find that partial label masking leads to performance gains on difficult classes which may contain many samples. For example, backpack, bench, and cell phone each achieve less than 21% F1 score when trained with binary cross-entropy loss, but have an average improvement of an 11% when PLM is used. This improvement is caused by the increase of the ratio for these classes during training, which leads to a corresponding increase in recall. Lastly, we examine partial label masking's effect on precision and recall. We find that the precision across the frequently occurring classes increases as PLM reduces the amount of overpredictions for these classes. This also leads to a drop in the recall for some of these frequent classes. The most notable change, however, is the large increase in recall across the tail classes. Using partial label masking drastically reduces the underprediction for these classes. For example, from the 5 least frequent classes, the recall increases by an average of 13%. This increase leads to an overall improvement in performance on the entire dataset. Thank you for watching my presentation on our work, partial label masking for imbalanced multi-label classification.